Hello, and welcome to the Big Bang Kilonova Hypothesis podcast. My name is Stuart McLean, and I am both your host and progenitor of said hypothesis. In this particular episode, I want to examine two new pieces of evidence that have come out over the last week or so, and it is getting things very, very exciting from my point of view. So, from my point of view, I'm trying to use a kilonova, the binary merger of two neutron stars, which gets birth to a rotational black hole, and which then, in turn, creates two new balloon universes that inflate from it. So, I'm putting a kilonova as the explanational cause of the Big Bang. And essentially, one of the most important things about Big Bang cosmology is the requirement for spherical symmetry, particularly within the very early stages of the Big Bang explosion. And the importance of it is really best put. So I'll read from The Primeval Atom by George Lemaitre, the introduction here, where he's describing the various chapters, and it just really shows the absolute importance that it plays, particularly within the mathematics. So in explaining the layout of the chapters, to quote, "Some mathematical explanations and notes have been added. They are divided into 3 chapters, each one being written for different classes of readers. The chief points are contained in the 2nd chapter. It covers the equation of Friedmann and various topics related to that equation. The 1st chapter deals with the theory of non-static fields having spherical symmetry, which is required to establish Friedmann's equations in the 2nd chapter." So Alexander Friedmann and George Lemaitre essentially showed that the universe was a consequence of Einstein's equations for general relativity, that it described an expanding universe. But part of that requirement is, as it says here, the theory of non-static fields having spherical symmetry, which is required to establish Friedmann's equations in the 2nd chapter. Paragraph goes on to say, the details of computation of Riemann's tensor are left for the 3rd chapter, where the student who wishes to check the theory in all its detail will find everything he may desire. So, as a quick side note, I'm doing a audiobook of this. This is an extremely rare book. I consider, for me, this is like The Origin of Species by Charles Darwin, or Newton's Mathematica Principia. I think that's how it's pronounced. But this effectively for me is, when it comes to the Big Bang and the 101 of the Big Bang, this book is the cornerstone of the Big Bang theory. This is George Lemaitre's book, and more specifically, it's the primeval atom. Primeval atom being a large neutron star. Of course, some of you may have noticed that it's been a small while since my last actual podcast, because I've been super busy. Been developing my latest film, Anatomy of a Kilonova, and this brings me onto the second part of what I want to discuss in this podcast, which is this. James Webb space telescopes uncover massive galaxies near cosmic dawn. Essentially, the Lambda CDM model says that there should be a dark age of cosmology. So if I just type in Lambda CDM model, and we just bring, it's really shown in this picture here. Zoom in on that. So we've got this part here, the number 3 dark ages. So between here, which is between the time 375,000 years after the Big Bang, you have the time of what's called the last scattering and the recombination, where electrons are binding with protons to form the first hydrogen atoms, because the plasma of the early universe has cooled down sufficiently enough such that electrons bind with protons, and thus the universe goes from being an opaque plasma to being translucent, such that photons of light can start the journey across the galaxy. But what the Lambda CDM model predicts is that because of the quantum fluctuations within here, they create upstanding waves which initially create small galaxies, which then grow and grow and grow and grow. So, and in that time, these small galaxies, which then form, or actually even predicting that the first stars are forming about 400 million years after Big Bang. So these particular ones are seen at 500 to 800 million years after the Big Bang. That's well within the dark ages, or where basically there's like large galaxy formations should not exist. However, to quote the work that I have been going at this day after day after day, building up this film, building up all the references, just building it, presenting everything, and I'm rewriting quite a lot of it. But it's really here in this very first paragraph. In beginning, I want to make a prediction based upon my proposed Big Bang Kilonova Hypothesis. That prediction being that the James Webb telescope is going to find spiral-shaped galaxy formations dating all the way back to the time of the last scattering and recombination of the now cosmic microwave sky, some 300,000 years after the Big Bang itself. We are going to find that the dark age of cosmology is not so dark as the Lambda CDM model would have us believe. Called it. I called it. Well, let's start with this. This is hard data. This is observational data that shows that the kilonova explosion, which is labeled AT 2017 GW170817, the GW being gravitational waves. So that's the optical naming of it. So that's the LIGO gravitational naming of the event, but the two go together. It shows that in the early epoch of the kilonova, essentially perfectly spherical from two independent point of views. So specifically, let's read the abstract. The mergers of neutron stars expel a heavy element enriched fireball that can be observed as a kilonova. The kilonova's geometry is a key diagnostic of the merger and is dictated by the properties of ultra-dense matter and the energetics of the collapse to a black hole. Current hydrodynamical merger models typically show a spherical ejecta, previously positive strontium ions, was identified in the spectrum of the only well-studied kilonova 2017 GFO associated with the gravitational wave event GW 170817. Now, this particular event was the binary merger of two neutron stars. So other events have been binary merger of a neutron star and a black hole, or black hole merger. But in my theory, I'm being very, very specific. It's two neutron stars. And the imprint of those two neutron stars, well, the two neutron stars of the superverse, you can see here and here. Or that's close fit, best fit model, but this is actual. This is the actual ESA published map. And we just scroll down here. The cold spot, what's known as the Eridanus supervoid, which existed 200,000 years after the Big Bang. Inflation theory says cold spots should take a long time to form, or large voids should take a long time to form. But we've got one cold spiral here, and one hot spiral here. You can see it more clearly in here. This is the best fit model, best fit to 11 years of WMAP data. First done by Jaffe et al., and then by McEwen at Imperial in college. Yeah. And I'm saying that's gravitational waves. So that's why I am, but I'm being very specific as well about a kilonova being a binary merger of two neutron stars, because also it involves the birth of what known gravitational singularity. A black hole neutron star merger, that's more, the gravitational singularity already exists. But the neutrons, so I want the birth of a gravitational singularity, such as because I'm assuming that at the very heart of the Big Bang is the birth of an unknown gravitational singularity. So I'm making the assumption of it being born, and that's causing me to use two neutron stars in my description. Also the other factor is these are also the same size. These two spots, they're the same size. It's not, if it was a black hole neutron star merger, I would expect one of these to be quite a lot bigger and the other one to be smaller. But they're the same size. But from a theoretical point of view, i.e. the requirements that are the spherical symmetry requirements that are required in order to make Friedman's mathematics work, when we require spherical symmetry. So sorry, but yeah, going back to this, and because this is hard evidence, where spherical symmetry in a kilonova, right here, hard evidence of it being seen. So previously, strontium ions was identified in the spectrum of the only well-studied kilonova 2017 GFO associated with the gravitational wave event GW 170817. Here we combine the strontium p Cygni absorption emission spectral feature and the black body nature of kilonova spectrum to determine that the kilonova is highly spherical at early epochs. So using one form of analysis, using the strontium signature, they see that it is highly spherical at early epochs. Line shape analysis, combined with the known inclination angle of the source, also show the same sphericity independently. So they've got two methods of finding whether what's the shape, what the symmetry of the shape of the explosion is, and both say it's spherically symmetrical. It's very spherically symmetrical. We conclude that energy injection by radioactive decay is insufficient to make the ejector spherical. A magnetar window jet from the black hole disk could eject enough energy to induce a more spherical distribution in the overall ejector. However, an additional process seems necessary to make the element distribution uniform. What would be that additional process? Been busy with artwork over the last couple of weeks. This one, I'll scale up a wee bit so you can see it better. So I'm doing a composition of, zoom out of there, so switch to that. So I've got my accretion disk around the black hole. So just prior to the kilonova, I've got the accretion disk, flat accretion disk that's formed out, and then you've got the two neutron stars spinning away, and then they merge, and then they collide. And then in turn they give birth to the black hole, which in turn these two entrapped manifolds of space-time, which then inflate like balloons. But they're being inflated at such a rate that I'm almost tempted to say they're being filled at a rate faster than the speed of light. Now here's the thinking on this one. At the event horizon of the black hole, the flow of space-time by definition is the speed of light at the event horizon of the black hole. Beyond the event horizon, where we pass into a temporal geodesic before coming out to the spatial geodesic of the wormhole, it's a rotate. So if I just bring up my map, bring up here's essentially the map of the multiverse as described by the Kerr metric. So it passed through into the black hole, and the matter passes through the wormhole now to the new universe. Actually, I'll show this animation here. So this is me trying to describe the inside what it looks like inside a black hole as best as I can possibly describe. We've got 6 quantum vortices here. The reason why 6 quantum vortices, why I'm using this particular argument, is a very delicate argument, which is essentially a large part of, essentially I have to describe most of this, describe the entire, how to describe everything right down to what a Bose-Einstein condensate is, and what we're seeing inside these Bose-Einstein condensates, what quantum irrotational flow looks like, which forms lattice-like structures. I should have some pictures of these here. This is what Bose-Einstein condensates look like down a microscope. We've got these this is what these black dots are quantum vortices, and in between is the probability wave that has been spread out in a Bose-Einstein condensate. So the matter in this is 1/1000th of a degree above absolute zero. And we find that there is this, what is called quantum irrotational flow. And as the rate of flow increases, the number of quantum vortices increases, rather than it behaving as, say, as a continuous rigid body which all moves in one, it is behaving in different little irrotational flows of quanta. And so that's what I'm describing here, along with the powerful magnetic field that gets generated inside. And then I've got like a sort of like, I've done a dark saber sort of look for the ringularity, but each of those feeds into the larger output, which is the white hole. And from the white hole, we get the balloon universe. So we've got the subverse, which then fills up with all these galaxies, and then inflates inside either, so for, in case of a subverse, inflates inside our universe, or in the case of talking about our universe is inflating inside the volume of the superverse. So big inflation, lots of galaxies. So that's one of my latest pieces of artwork, essentially describing all that principle. But in creating the artwork of the very early epoch, so right after these two collide, the black hole is born. It's going to be got to do lots of animations about all the intermediate steps in between that. But essentially, you have this entrapped manifold of space-time in the center of the ringularity, which then gets, and because the inflow of space-time is in towards the black hole, it gets sucked down, pulled through and injected out into this entrapped volume that is the white hole. And so I'm trying to do an animation of this expansion. So yeah, I'm doing an animation of this expansion across the accretion disk, where it keeps its spherical symmetry. And the reason it's keeping its spherical symmetry is because the rate at which, because I'm saying the electromagnetic field is essentially being torn apart, such that it blisters and into these blisters, these two balloons of entrapped space-time are being filled up with quantum gluon plasma, which I'm trying to give using a sort of a fluid simulation to try and capture. So I can So this fills up and expands spherically because essentially, but the rate at which it can expand, I've got two ideas about it. I'm wondering, I mean, it's filling up at, I would say at a rate faster than the speed of light, because beyond the event horizon of the black hole, things are being pulled down. Poof, poof. So the flow of space-time beyond the black hole is faster than the speed of light by definition. And then through the singularity, out through the white hole, and then this is filling up faster than the speed of light, but still inside our universe. The rate limit of the electromagnetic field is the speed of light, so it can't expand faster than the speed of light. So you've got this massive pressure here coming from the inflow from everything that the kilonova has eaten, and the rate at which anything can expand, this new subverse can expand, and it cannot expand faster than the speed of light, even though the material being injected into it is probably going faster than the speed of light after it travels through when it's being ejected from the white hole. That's my kind of reasoning around. That's my general reasoning around it. So in that one thing there, I've got a reason for why the Big Bang had spherical symmetry. Is the rate at which our universe could expand could not exceed the speed limit of the superverse. Well, and I'm assuming this, so effectively the rate at which a photon of light of the superverse can move across the electromagnetic field of the superverse, which to us, when torn apart, is, and we're inside it, to us that is our gravitational field. So that that right there is a major win. The actual paper for it is here. I could try, as part of me wanting to kind of think, I could try and read through this. Really, it is very specialized, specific analysis. But effectively, as the abstract says, the mergers of neutron stars expel a heavy element enriched fireball, which can be observed as a kilonova. The kilonova's geometry is a key diagnostic of the merger and is indicated by the properties of ultra-dense matter and the energetics of the collapse to a black hole. Currently, hydrodynamic merger models typically show a spherical ejecta. Previously, strontium ions was identified in the spectrum of the only well-studied kilonova, AT 2017 GFO, associated with the gravitational wave event GW170817. Here we combine the strong strontium P Sigma absorption emission spectral feature and the black body nature of kilonova spectrum to determine that the kilonova is highly spherical at early epochs. That's very critical, at early epochs, so meaning right after the kilonova event. So So I make sure I'm doing my artwork to have this spherical explosion. So I have one here, and then have another one on. Then I'll probably mirror this object such that I have it under here to show the universe, our universe, our parallel universe of antimatter, or the parallel universe for a given subverse. And the two effectively inflate out to the point that it is that creates a sphere, essentially creates these two spherical subverses in the early epochs following the kilonova event itself. Yeah, currently working on that artwork, but I'm working on it because so we've got one way of knowing about how it's highly spherical. The other way, line shape analysis, is combined with the known inclination angle of the source, also shows the same sphericity independently. So take the method one way and now using another method. We conclude that energy injection by radioactive decay is insufficient to make the ejector spherical. A magnetar wind or jet from the black hole disk could inject enough energy to induce a more spherical distribution in the overall injector. However, an additional process seems necessary to make the element distribution uniform. That additional process being accounting for the expansion of the subverse within the volume of space. I mean, the traditional view has always been that these new universes are completely separate to our universe. They're somewhere else. They're outside our universe. They're their own bubbles of space-time. But rather, I say that they are entrapped surfaces of space-time, just as a black hole is an entrapped surface of space-time, which entraps the wormhole, which entraps the white hole, which then entraps these two balloon universes, which, like bubbles, grow inside our universe, such as we see given the glow of the Fermi bubbles. And the importance of spherical symmetry, it is really critical to the big. It really is critical to the Big Bang, and as critical, quoting from Lamarck's book, the first chapter deals with the theory of non-static fields having spherical symmetry, which is required to establish Friedmann's equations in the second chapter. So an entire chapter of Lamarck's book called The Primeval Atom, essentially this is Big Bang 101. This is where it all began, the idea of the Big Bang. There's an entire chapter dedicated to the importance of spherical symmetry. And that is hard evidence of spherical symmetry in a kilonova. That's one thing. Then there's the other thing, as I was pointing out at the beginning. In beginning, I want to make a prediction based upon my proposed Big Bang Kilonova Hypothesis. That prediction being that the James Webb telescope is going to find spiral-shaped galaxy formations dating all the way back to the time of the last scattering and recombination of the now cosmic microwave sky, some 300,000 years after the Big Bang itself. We are going to see the dark age of cosmology is not so dark as the Lambda CDM model would have us believe. I just want to find a particular animation showing fragmentation from a kilonova. Oh. So I've got some animations where I'm thinking about how does it fragment apart and fall together to such that a black hole is born. Just using one electromagnetic field. This is the pattern of distribution you get from you get I get from creating a particle system. So you've got the material being thrown out, but then in the middle you've got the material that's being sucked into the black hole, and then you've got the other material which then goes along to form these thin short gamma ray bursts. And so as the two neutron stars effectively collide, they shatter each other, and at one end of the spectrum you've got quark gluon plasma, and at the other end you've got this fragmentation of, well, the material inside the neutron star is the strongest stuff in the universe. It's 400 quintillion times stronger than steel. 400 quintillion. That's like 1,000 trillion, which is a million billion. Stronger than steel. So to shatter it, but then also you've got in the core the quark gluon plasma. So it's not one or the other. It's an equal both. You're going to have so essentially you have a quark gluon plasma interspersed with grains of very dense material which are fragments of the neutron star, which probably like sugars, like probably like grains of sand, but they're not. But essentially, these grains of sand. Let's think of it as grains of sand. But these grains of sand to us flow into our universe from the very beginning, and they become to us the supermassive black holes. So that's the important point. One thing that the lambda CDM model fails to take account of, the explanations are just so below par that everyone is. I get the feeling that most of the cosmology knows that, yeah, we're kind of going along with this because it's the best we've got. I've got better. Big Bang Kilonova Hypothesis. And from that, you've got, and it counts for super birth of massive black holes, these the fragments, which are the fragments of the neutron star, and they to us become the supermassive black holes that sit at the center of every galaxy. And they're there from the very, very beginning, even before they actually go through into the black hole, out through the rotational white hole, and into our early universe. They're there from the very beginning, and because they're there, they start feeding from the very, very beginning. And so, because they're feeding from the very, very beginning, you're getting disc-shaped galaxies being formed even before the time of the last scattering and recombination. And because of that, I am saying that's what causes me to say I make this prediction. I want to make a prediction based upon my proposed Big Bang Kilonova Hypothesis. That prediction being that the James Webb Telescope is going to find spiral-shaped galaxy formations dating all the way back to the time of the last scattering and recombination of the now microwave sky, some 300,000 years after the Big Bang itself. We are going to find the dark age of cosmology is not so dark as the Lander CDM model would have us believe. Let's have a read through this article here. I mean, that's one kill. This is another. And I just got to the point I've probably got about a third of the way through it. So I've described the structure of the neutron star in exquisite detail, such that I can then begin to describe the exact sequence of the kilonova as told from the point of view of my hypothesis, along with presenting as much evidence particularly from this one event. But then in turn, that allows me to build up the argument that I then present about you've got your quark gluon plasma, but you've also got these grains of the super neutron star that are coming into our universe. These super compact things, they are the supermassive black holes. And why are they supermassive black holes? Well, because they're formed from the mass of the super neutron star. The two super neutron stars of the superverse, because everything's just super in the superverse, because you just prefix it with the word super because it's just so super. But these supermassive black hole, I mean, a neutron star in our universe, a sugar, a spoonful of it, a teaspoonful, it's like a teaspoonful of sugar. If you replace that the sugar with neutron star matter, it would weigh the same as Mount Everest. That's like 5 billion tons. It is a massively heavy object in such a small condensed area. And that's why you got supermassive black holes in our universe from the very beginning. I called it, and let's get on and read this article. Space telescope uncovers massive galaxies near cosmic dawn. Cape Canaveral, astronomers have discovered what appear to be massive galaxies dating back to within 600 million years of the Big Bang, suggesting the early universe may have had a stellar fast track that produced these monsters. While the new James Webb telescope has spotted even older galaxies dating to within a mere 1/300 million years of the beginning of the universe, it's the size and maturity of these 6 apparent mega-galaxies that stunned scientists. They reported their findings Wednesday. Lead researcher Ivo Labam of Australia's Swinburne University of Technology and his team expected to find little baby galaxies this close to the dawn of the universe, not these whoppers. While most galaxies in this era are still small and only gradually growing larger over time, he said in an email, there are a few monsters that fast track to maturity. Really? Why this is the case or how this would work is unknown. Unknown? Oh, sorry, did I just give my explanation? Each of the 6 objects look to weigh billions of times more than our sun. In one of them, the total weight of all its stars may be as much as 100 billion times greater than our sun, according to the scientists. who published their findings in the journal Nature. Here's the actual paper, Nature, or here's the actual full paper. All links to, as always, I'll put into the comment. I'll put into the description. But I'm certainly going to be going through this in quite a lot of detail. Maybe in future episodes, or I'm mainly concentrating on my film at the moment, but there's some nice shots there of like the different spectral lines. I really want to. So yeah, I'm really trying to. Putting the whole thing together, I'm good at. I'm still like come to operating a telescope. I've still got to learn a few things. Each of the six objects looks to weigh billions of times more than our sun. In one of them, the total weight of all its stars may be as much as 100 billion times greater than our sun. According to the scientists who published their findings in the journal Nature, 100 billion times greater. How many stars are in the Milky Way galaxy? 100,000 million. So 100 billion. $100 billion times 100 billion stars. So greater than our sun. So the size of the Milky Way. So these monsters are the size of the Milky Way galaxy. If they're 100 billion, I mean, we've got 100 billion stars in the Milky Way galaxy. 100 billion stars. The point. Yet, these galaxies are believed to be extremely compact, squeezing in as many stars as our own Milky Way galaxy, but in a relatively tiny slice of space, according to Lamb. Yeah. Yeah. You can see I pick up on these things very quickly. Lamb said he and his team didn't think the results were real at first. Oh, I do. That there couldn't, which makes it even better because they're going to really work overtime to confirm that their results are valid, and they're going to do that and do that and do that. And the more they do that, and the more valid those results, the better it is for me. That there couldn't be galaxies. Sorry. Lamb said he and his team didn't think the results were real at first. That there couldn't be galaxies as mature as the Milky Way so early in time, and they still need to be confirmed. The objects appear so big and bright that some members of the team thought they had made a mistake. We were mind blown, kind of incredulous, Lamb said. The Pennsylvania State University's Joel Ledger, who took part in the study, calls them universe breakers. The revelation that massive galaxy formation began extremely early in the history of the universe upends what many of us have had thought was settled science. Ledger said in a statement, "It turns out we found something so unexpected it actually creates problems for science. It calls the whole picture of early galaxy formation into question." So if you want to read about early galaxy formation, the current document is this one. Podcast 3, Anatomy of a Kilonova, particularly towards the end. Though right at the very end, well, the King's Coronation's coming up. I hope to get my film finished for time for the King's Coronation. You'll see why. And if that sounds ominous, there's ominous, and then there's this. Grill, 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 grill. I've had up to here with grills. Well, actually, I seem to have developed a very great streak of luck all of a sudden. Not that I'm going to go down the gambling shop, because as soon as I try to guess lottery numbers, yeah, that's where it's going to fail. The revelation that massive galaxy formation began extremely early in the history of the universe upends what many of us had thought was settled science, Ledger said in a statement. It turns out we found something so unexpected it actually creates problems for science. It calls the whole picture of early galaxy formation into question. These galaxy observations were among the first data set that came from the $10 billion Webb telescope launched just over a year ago. NASA and the European Space Agency is considered the successor to the Hubble Space Telescope, coming up on the 33rd anniversary of its launch. Unlike Hubble, the bigger and more powerful Webb can peer through clouds of dust with its infrared vision and discover galaxies previously unseen. Scientists hope to eventually observe the first stars and galaxies formed following the creation of the universe 13.8 billion years ago in the Big Bang Kilonova explosion. Sorry, ad-libbing there. The researchers still are awaiting confirmation through sensitive spectroscopy, careful to call all these candidate massive galaxies for now. Ledger said, it's possible that a few of the objects might not be galaxies but obscured supermassive black holes. While some may prove to be smaller, odds are good, at least some of them will turn out to be galactic giants, Labid said. The next year will tell us. One early lesson from Webb is to let go of your expectations and be ready to be surprised, he said. Well, so on two fronts, to close up this episode. First front is hard evidence of that a kilonova has the requirements for the Big Bang as described by Alexander Friedman's work, The Importance of Spherical Symmetry. I'm hoping to have the first chapter in the introduction of George Lemaitre's Primeval Atom up very shortly. And of course, the first chapter, as it says in the introduction, is dedicated to the importance of laying out the conditions for spherical symmetry. That's one front. And then these 6 galaxies, which should not exist according to the Lambda CDM model, but according to the Big Bang Kilonova Hypothesis, should exist. Because black holes are fragments of the superneutron star that entered into our universe from the very, very beginning. They're not, because they were there from the very beginning. They began to feed on the surrounding plasma, and that drew more in, and such that spiral elliptical galaxies very quickly formed within the plasma, effectively between the time of the first epoch, to give it its classic name, to the time of the last scattering and beyond, and lit up the dark ages. And it's saying first stars about 400 million years. Well, we've got stars going back to 300 million years. The data is piling up against the land of CDM. And it's just going to pile and pile and pile. And what was it, the other... I mean, even the last podcast, I was like, oh, look, new evidence about the CMB dipole that's in my favor. And I've still got... I mean, that's going to be a whole film in itself after this one. But, yeah. It's... the evidence is building up on my side and building, and it's only going to build, and it's only going to build. Formation of early galaxies in the universe. Called it. And with that, I'll catch you next time in the Big Bang Kilonova Hypothesis podcast. Until next time.